I'd like to show you now an experiment that we did here in the physics building at University of Texas, in which we rode up and down in an elevator and watched what happened to our weight. We stood on spring scales as the elevator was riding up and down in the building, and we should know that as we get started, the spring scale tells us basically what is the force of the floor pushing up on our feet. When we go stand on a spring scale in our bathroom, it's often the case that we're sitting still, and as a result of sitting still, our acceleration is 0, and we know that the forces on us are balanced. We have the equal force pulling down, that's gravity or our weight, and we have it's equal to the force pushing up, which is the floor. So since the spring scale measures the force of the floor, we use it as a measure of our weight. But what we're going to really learn is that the force of the floor isn't always the same as just our weight. So this experiment will show us how the force of the floor has to change as an elevator is moving up and down.
Okay, so his weight's 149, and the elevator is we're gonna go up first. So there's gonna be an initial change in speed when we start to move up. And he's gonna watch what happens to the scale during that initial change in speed. Went up to 160. Okay, went up to 160. Now we're moving at a constant speed, and what's your measurement right now? 149. 149. Okay, we're going to slow down in a second. Let's see what happens. Went to like 145. Down to 145 while we're slowing down. Okay, now we're going to do the same thing in reverse. We're going to go down. There's going to be an initial change in speed, and we're going to see what happens during the initial change in speed. It went down to about 140. Down to 140. And we're going at a constant speed right now. What is it? 149. 49. We're going to slow down in a second. 160. Went up to 160. Okay. Everyone get all those?
In our experiment, we used direct measurement to see what was happening to the weight or our apparent weight, which was on the spring scale, which was really the force pushing upward on us from the floor. You can tell this wasn't actually me, because unfortunately I don't weigh 150 pounds, but the student who stood on that scale observed a complex set of events where his apparent weight, or actually what I will have to keep saying is the force upward on his feet from the floor, changed throughout the elevator ride. Let's try to model this now, this sequence of events as it transpired in the video. And in this, we will start with what we think must be the acceleration and use that, the set of facts about what's happening to the acceleration to deduce what must be happening to the force from the floor. We started out at rest in this elevator. At rest means the velocity is 0, and as a result, the acceleration is 0. And in this case, we saw that the student's weight was his typical or normal value of 149 pounds. Since his velocity was 0 and his acceleration was 0, most importantly his acceleration, the forces on him are balanced. So if the green arrow here represents the force of gravity, his weight, then the force upward on him, the blue arrow here from the floor, the so-called normal force, must be equal and opposite in magnitude. So from here on out, I'm going to use green arrows and blue arrows to indicate what must be the two forces acting on the person in the elevator. In this case, they were equal when at rest. But the first step in this sequence of events was that the elevator started out from rest and started accelerating upwards. In this case, the velocity was positive and the acceleration was positive. Both were heading upward. If they are to be represented as vectors or arrows, they're both pointing in the upward direction. If the acceleration is positive because we're speeding up, then what must be the case is that the net force, by Newton's second law, is also pointing up. The net force is a vector, and it is the sum of two vectors. It's the normal force from the floor and the person's weight pulling down. The person's weight hasn't actually changed. Gravity is still the same on this person, so what must be the case is that in order to get the net force being pointing up, the force from the floor has to increase in magnitude and still point up. So this is why he reported that his weight jumped up to something more like 160 pounds instead of 150 pounds. It did so because the force from the floor had to increase in order to start accelerating his mass upward. The next set of events, was that the elevator was moving at constant speed. In this case, the velocity was still positive, but there is no acceleration. If you're moving at constant speed, there is no change in speed, and therefore acceleration is zero. In this case, if acceleration is zero, the forces must be balanced. And what we saw is exactly that the spring scale recorded his normal weight again of 149 pounds, and that's consistent with our picture of Newton's second law predicting that the net force is zero. In other words, the force up from the floor equals the force down from gravity. He saw his normal weight. The last step in the person's trip to the upper floor of the building was that the elevator has to slow down and come to rest at the upper floor. Well, what happens in this case? The velocity is still pointing up, but acceleration is negative. In order for speed to be decreasing, or the elevator to be slowing down, the acceleration vector has to point in the opposite direction to the velocity vector. This is how we know from our kinematics days we can get speed decreasing. It has to be a negative acceleration. Well, how do we get a negative acceleration? By Newton's second law, the net force must point in the negative direction, or down. And again, the force of gravity has not changed. It is still pulling down with the same value, mg, m being the person's mass. So in order to make this case where the net force points down, the force from the floor has to be smaller in magnitude. So miraculously, he reads a smaller value on the spring scale because what's happening is the force of the floor is smaller than typical. He read a number more like 140 pounds. Next began our trip to the lower floor from the upper floor of the building. Once again, we started at rest and we saw the person indicate his normal weight on the spring scale. And that's because when at rest, the acceleration was zero and the forces are balanced. The force of gravity pointing down is equal to the force of the floor pushing up, and the force of the floor was the typical value, 149 pounds for this particular person. But then the elevator started moving down, its velocity became negative, and in order to speed up, the acceleration has to be negative as well. For an object to start speeding up, the acceleration vector has to be in the same direction as the velocity vector. Well, how do we get an acceleration that's negative? In order for that to be the case, by Newton's second law, I must have the net force be negative or pointing down. Newton's second law is a vector equation, and in whatever direction the acceleration vector is pointing, that's where the net force is pointing. Once again, the weight has not changed in magnitude. Only the components of the force that are changing are the force of the floor. So the force of the floor got to be smaller, and that gave me a net force pointing down. When the force of the floor is smaller, his weight looks smaller, and indeed he saw a number close to 140 pounds when he started moving down. The next step was that the elevator was moving at constant speed in the downward direction. That means that the velocity is negative, but most importantly, the acceleration was zero. If the acceleration is zero, the forces are balanced again, and the force of the floor equals mg. So he read off the scale his normal weight. The last step in the sequence was the elevator still heading to the lower floor but slowing down as it comes to a stop. This means that the velocity is negative, but the acceleration vector has to point in the positive direction because that's how we slow down. The acceleration vector has to point in the opposite direction as the velocity vector. This means that the acceleration is positive and the net force has to be in the positive direction. The weight, the green arrow here, has still not changed in magnitude, and therefore the force of the floor has to be much larger. And as we saw, he read off a scale value of 160 pounds, so he gained 10 pounds. So the whole sequence of events here merely told us what was happening to the force of the floor. It didn't really record changes in his actual weight. Merely what the floor had to do to either accelerate or decelerate his mass. As a final step of this presentation, I want to ask, what would you imagine the spring scale would read if the cable in the elevator broke? If the cable in the elevator broke, sadly, we know that we would go into free fall. We would be accelerating downward at a value g. If we're accelerating downward with value g, that means that the only force on us is gravity, and it's pointing down. There's nothing pushing up. So there's no force of the floor at all. The normal force is 0. If the force of the floor is 0, the scale will read 0. And although we'll be weightless, at least we'll feel weightless, we know that when we hit the bottom, something very negative is going to happen. But actually, this is the kind of experience that astronauts in training go through. They fly in the upper atmosphere in these very large airplanes that go into temporary free fall, these parabolic trajectories that try to simulate for the astronauts weightlessness by essentially having the plane fall for a short time.